Hello and welcome to my presentation on zero shot text to image generation. I am Saptarshi Mukherjee and I will be describing this topic as a part of my DA323 final project. So now about the motivation for this project. Text to image synthesis, as we know, it is one of the most interesting applications of deep generative models. It requires a deep understanding of language and the ability to create visual representations. So I found it quite interesting because it blends vision and technique in language in quite a unique way, with byte pair encoded text tokens and discretized image tokens. So discretization of image tokens is quite a new thing, which is what drew me to this topic. So if we look at some early efforts in this domain, then we can find things like conditional GANs and conditional variational autoencoders. Their main issue was that they produced blurry or semantically mismatched images due to the limiting modeling capacity. While stack GAN, they had a two-step generation process: first a low resolution image and a high resolution image after that. Attention GAN, it improved by introducing word level attention. So here the generator could focus on relevant words while generating specific regions of the image. So the outputs were more coherent and better aligned with fine-grained captions. The main limitations of earlier models was that we needed paired datasets, which is that we needed image caption pairs. Here that is not necessary, as uh, we just compress images into discrete tokens and then we train a transformer on the joint distribution of text and image. So it enables zero shot generalization without first fine tuning on specific datasets. So the pipeline is as follows: we pass the image to a decoder. We also encoded get a 32 cross 32 grid, which we flatten to get a 1024 set of tokens, and then we also encode our text tokens using byte pair encoding. So that is just a kind of compression technique. We concatenate them together and apply a transformer. So the transformer uses self-attention and other mechanisms to learn the distribution between the image and the text tokens, and this in turn is applied to the VAE decoder to produce our output image. So now a little more about the paper. So the authors of this paper are Ramesh, Pavlov, and Go and Gray, and several others, including Ilya Sutskever of OpenAI. This was published in February 2021, and the core contribution of this paper is a scalable autoregressive transformer based model which treats image and text tokens as a single sequence. So another advantage of this is that it can generate images from text prompts without any task specific fine tuning. So like I said, the first high resolution images are compressed into discrete tokens. Then each 256 cross 256 image is converted into a 32 cross 32 grid of tokens. Each token has 8192 values. So one thing we can notice in the example reconstruction, if you notice, the top images are the original and the bottom ones are the reconstructed ones. So you see that the text gets a little blurry, and the exact texture of the cat's fur, it gets blurry, and the lines also, you can see these lines are hardly visible below. Okay, so now I will describe the objective function and its interpretation. So the model wants to learn the joint probability of the text prompt image and the latent image tokens from the discrete VAE. This distribution can be modeled in this way. And now, since we cannot really optimize a joint probability, there are no real algorithms for that. We take the help of the evidence lower bound. This is quite common in encoders, especially variational autoencoders. So hence it is used here. So the first term here indicates the reconstruction loss. So it is kind of a measure of how good the encoder is at reconstructing the image. While the second part is scale divergence, and what it does is that, as described on the next slide, it is primarily a regularizer. So in the regular autoencoders, it prevents the DVAE from encoding gibberish. It also helps to ensure that the autoencoder, it does not simply memorize the input images. So you can kind of say that it helps us to ensure that there is variation in the outputs, which would not happen if it had simply memorized the images. So now a little bit about the architecture of the autoencoder. So it uses convolutional ResNets with bottleneck style residual blocks in both the encoder and the decoder. Although most layers are 3 cross 3, we also have some skip connections which use 1 cross 1 convolutions at the end and at the beginning of the decoder and encoder. And at the end, we output 32 cross 32 cross 8192 logics, which we can understand based on the dimensionality of the image tokens, which I talked about earlier. Max pooling is used in the encoder for downsampling, while training is done using the Adam W optimizer. As for the transformer, it is a 12 billion parameters. So this is a really large transformer with as many as 12 billion parameters. It takes a sequence of up to 256 byte per encoded text tokens and 1024 image tokens. So we have causal self attention. So it does not allow uh, an image token to attend to anything which is later on. So it can only attend to things which are earlier. Okay, so those we use specialized attention masks for this, and we just generally set the later tokens to minus infinity so that they are not taken into account while computing attention scores. So we have specialized attention masks for the images like and text. So causal mask for text and structured row column convolutional masks for images. This model can perform zero shot generation. So a little bit about the data set. So a massive data set of as many as 250 million image text pairs was collected because we need to train a very large model. So obviously we need a lot of image text pairs. It is comparable to JFT 300 million, and it is significantly larger than COCO. So although their captions were not directly used, there was still some overlap. So captions that were actually too short or they were not in English, so they used a library to detect that, they were removed. And the generic or boilerplate captions like photographed on a particular date, they were also discarded. And images with extreme aspect ratios were also excluded to preserve visual content during training. So one thing to note is that this dataset was it's a much larger dataset compared to COCO or CUB 200. So the authors, what they want to demonstrate is that better performance can occur if you have more data and you have more model size, like in this case. So it was evaluated in a zero shots setting without any fine tuning. It was compared against other state of the art models like attention GAN, DM GAN, and DF GAN. DF GAN had earlier reported the best inception score and a fresher inception distance score. So quick word about the score. So what it does is that inception score is a measure of how diverse the generated images are, and fresher inception distance, it kind of measures the distance between the distributions. So the distance between the generated image distribution and an input distribution which you are providing. So obviously we will want a higher inception score and a lower FID score. So how is this evaluation done? So a human might be given a task like this. So he is asked which of these two images is more realistic and which image matches with this caption better. So the caption here is a man walks across the street with a stop sign in the foreground. So we can see these two images and the human will have to select which one is better. So if we look at the results, so notice that that their model, the authors of the paper, they discovered their model is chosen as the most realistic as much as 90% of the time, and a pretty big chunk of this is unanimous actually. So it is quite a lot better than DF GAN on both realism, so as to how real the image looks like, and even on accuracy. So how accurate is the image respect to the shared caption. We can see some of the images here. So we can see a very cute cat laying by a big bike. So this model we can see is quite accurate. We can see the bike and the cat itself. In DF GAN the bike part is not that clear, and in DM GAN is the same thing. So we can see similarly like China Airlines plane on the ground with baggage cars nearby. You can see that their model does indeed have that, while the other models can be a little not sure about this, like DF CAM and DM GAN, none of them they include the plane wing. So we can kind of think that their author's model actually performed quite well across all the tasks if we can take a look. So now on the CUB dataset, so the CUB dataset, it is a specialized dataset which has for example bird images or other nature images, and on this dataset however this model performs significantly worse. So it has as much as a 40-point gap in FID. So if we think about why, it could be because the zero shot model, it struggles with specialized datasets. So we might have to do some fine tuning in order to use our model on this. So some of the things I learned from this paper are that we can even frame image generation as language modeling, and we can use the transformer to use attention and train it on the dataset to generate high quality images. So we can think about image synthesis to be a token prediction problem rather than a pixel modeling problem. So it kind of bridges the gap between image computer vision and natural language processing quite a bit. So discrete representations, they simplify image modeling in this case, and text and image fusion, they may not always need explicit alignment. Here they are just concatenated and The transformer learns the multimodal relationships on its own, and we might even be able to do zero shot generalization if we train on a large enough web dataset even without proper supervision. Some of my reflections are like token granularity and positional encoding, they really matter because here, unlike other models, they use structure attention masks. It was a subtle but crucial trick to help the model reason spatially. And I was initially also quite skeptical about how discrete image tokens actually might work, since especially since there's always a chance that the autoencoder it might not be able to reconstruct the image as well, but the model is still generating very high quality images. So we can think that the abstraction is simply, it is still retaining enough information for generating the images. So the zero shot capability is also quite surprising. Like it can generate semantically meaningful images even for captions it was never trained on. And there is very little inductive bias as well. Like there is no explicit alignment module or there is any segmentation supervision or anything, yet the model still learns how to do this. So now let's take a quick look at the code demo. So let me open the, yeah. So if we take a look, so I tried to implement the variational autoencoder part of the model because training a transformer is quite tricky and it would have taken too long. So I have this regular convolutional layers. I have this code book which has certain number of layers, and then we pass the image through the encoder, and we pass it through the code book to generate proper encodings, and we also try to reconstruct the image. The loss function next, it tries to balance three objectives, which is the image reconstruction accuracy, the embedding quality, and the commitment of the decoder, how well it makes the codes discrete. So I'm going to use it on the CFAR 10 dataset, and I'm going to train it for 50 epochs with the Adam optimizer. And once we do this, we can see that the loss, it actually jumps around a little bit. It doesn't decrease that linearly, and we can visualize the images and the reconstructions, and we see that the image generation accuracy, it's not bad, but likely using a larger model would have helped, but it's difficult to do it on the free Kaggle membership. So now I will also visualize some of the learned tokens. So you can see that these were some of the tokens learned. So we can see there is quite some difference between the tokens, as in no two tokens appear very similar. So now I'll also visualize what it will look like to have the image and its token, all of its token IDs side by side. This is the regular image and these are all of its token IDs. So here the autoencoder, it does learn a way to encode the old image into a set of token IDs like it was done in the paper, and this is the reconstruction result we are getting using this. Keep in mind that this was quite a simple model I used. So uh, yeah, so as you can see, it does not have too many layers, only three convolutional layers in the encoder and three in the decoder. So I was trying to demonstrate how it works without incurring too much GPU time. So this is kind of how it works. It has an encoder, it has a code book to discretize the image, it has a decoder which samples and reconstructs the image, and the tokens which were visualized, they are basically what is seen in the code book here. Okay, so that was the code demo. Now, talking about the future impact of the paper. So this paper, it sparked a revolution. It directly inspired a wave of groundbreaking models. So we the model we are quite familiar with, the DALI 2. So it uses clip also along with so we know that clip uses contrastive loss, like we already seen. Models like Imagen, they use some kind of large language model along with along with diffusion. So it's quite similar to this model in some sense. And the stable diffusion, the famous open source latent diffusion model, it was also inspired by this model. Yeah. No, that is it for the explanation. Thank you.